Hello, it's Dr. Daystorms again, and now we're going to conclude Chapter 3 by looking at how to use chemical equations. In particular, we're going to focus on limiting reagents, theoretical yields, and percent yields. In the end, we'll also discuss 3 of the common types of chemical reactions that occur. So, this portion of the chapter deals with a term called Stoichiometric Calculations, which sounds really scary, but in reality, all of that means is that the quantity or the amount of reactants that you have will dictate the maximum amount of products that you can make, which is really common sense. And the stoichiometry is a fancy way of just saying, looking at the coefficients and look at the ratio of how many reactants and how many of each type of reactant will make how many products. And finally, we'll talk about limiting reagents, the theoretical yield, and percent yield. So let's look at an example. You can actually consider a recipe as being a chemical reaction, because in reality, you have 1 cup of peanut butter, that's a reactant. It reacts with 1 cup of sugar, reacts with 1 large egg, so we have 3 reactants. You add it, and you mix them together, you add heat, the reaction occurs, and you get a product. We get 12 cookies. So let's start and transform this into a chemical reaction. So now we have 1 ratio of peanut butter. So the stoichiometry is 1 to 1 egg to 1 sugar. 1 to 1 to 1 to 12. So 1 of each of the reactants will combine to make 12. This little symbol here, the triangle, just means heat. So how many cookies can we make if we had 3 peanut butters, 3 eggs, and 3 sugars? Since it's 1 to 1 to 1 to 12 is the stoichiometry, 3 to 3 to 3 will make 36. We can make a maximum of 36 cookies in this scenario. So let's try something that may be a real-world example here, at least in my kitchen. Here, we have 2 cups, or 2 units of peanut butter. We have 3 eggs. And we have, in case you can't tell from the picture, but we've got 4 cups, or 4 units, of sugar. Now it's no longer 1 to 1 to 1, which is what the recipe, or the chemical reaction, calls for. So at most, we're going to run out of and use up the peanut butter first. This is called the limiting reagent. The peanut butter is a limiting reagent here. So since we have 2 cups of peanut butter, we're going to use up a maximum of 2 eggs, so we'll have 1 egg left over, and 2 cups of the sugar, and we'll have 2 cups of sugar left over. The maximum amount of cookies that we can make from this scenario would be 24 cookies. Since the limiting reagent was 2, and it goes from a ratio of 1 to make 12 cookies. That means that 2 cups of peanut butter can make 24 cookies. Uh-oh, something happened, and we only made 20 cookies because of some mishap in the kitchen. I don't know about you, but I'm starting to get hungry for some peanut butter cookies. Here, though, we can determine what's called the percent yield. The percent yield is when you take your actual amount, in this instance, 20 cookies. You divide it by what's called the theoretical yield, which is the maximum amount that you could make, which was 24. So the actual divided by the theoretical. You have to multiply by 100 in order to make it a percent. And we come up, in this instance, we had an 83% yield. This is a very important concept to master and to understand, because you're going to be using it throughout chemistry and throughout organic chemistry, for that matter, in many labs. So now let's look at a more scientific approach to this. I didn't want to start off with this because just throwing at you it may be a little more confusing. But we can actually use stoichiometric calculations to go from a given, like grams of a substance of A, and determine how much product it's going to make, product B, or maybe how much of the other reactants it's going to use up. But you can't go directly. Notice we can't go directly from grams to grams. You can never do that. You have to go from grams to moles of A using the molecular weight or the molar mass. Then, based off of the coefficients of the balanced, that's the important part there, the balanced chemical equation, you can go from moles of A to moles of B. Then use the molecular weight of B to find out the total grams of B. So let's do some examples. This right here is looking at the combustion reaction of glucose, which is a sugar, when it burns with oxygen to make carbon dioxide and water. So let's say that we want to find out how much water is going to be made from 1 gram of glucose. There isn't a direct way to go from glucose to water, grams of glucose to grams of water, I should say. So instead, we're going to use the molecular weight, which if you look at the periodic table to get the atomic weights for each of the elements, you're going to find out that the molecular weight of glucose here is 180 grams. So when we convert that to moles, we're going to find that we have 5.56 times 10 to the minus 3 moles of glucose. Now we can convert that into the number of moles of water. Since 1 mole of glucose will make 6 moles of water, that means we're now going to be able to make, theoretically, 3.33 times 10 to the minus 2 moles of water. Finally, we want to convert that number of moles of water to grams of water by using water's molecular weight, which is roughly 18 grams per mole. So by multiplying by 18 and dividing by 1, we're going to find out that the maximum amount, the theoretical yield, it's called the theoretical yield once again, would be 0.600 grams. If that's the theoretical yield, then what would be our percent yield if we only made 0.400 grams of water? So let's find the percent yield. This is the theoretical yield, which I'm just going to abbreviate as TY. Let's find our percent yield. To do that, we would take the actual yield, 0.400, divide it by the theoretical yield. Theoretical yield, 0.600, and multiply by 100. I'm going to erase this over here to put my answer. Okay, so 0.4 divided by 0.6 times 100 is going to come out to 66.7%. Let's do another example. Here we have solemn lithium hydroxide, and it's what's used in space vehicles to remove exhaled carbon dioxide, because otherwise the astronauts would suffocate. They would run out of oxygen. Okay? So the lithium hydroxide reacts with the gaseous carbon dioxide to form carbonate in liquid water. How many grams of carbon dioxide can be absorbed by 1 gram of lithium hydroxide? Interesting. First off, we need to make a balanced chemical equation, which I'm going to go ahead and give you that answer. The balanced chemical equation is as follows. It's 2 lithium hydroxides plus 1 carbon dioxide reacts to form lithium carbonate plus 1 water. Sometimes the hardest part is just trying to figure out what this question is asking for. This question is asking how many grams of carbon dioxide can actually be absorbed if you have 1 gram of lithium hydroxide. It's actually not asking about the products. It's asking how much the carbon dioxide can be removed from the atmosphere, from the environment of the space vehicle, the spaceship. So, we made our balanced chemical equation. Next up, we have to just go for our plan of attack. Really, now what we're wanting to do is go from grams of the lithium hydroxide, and we can't go directly to grams of carbon dioxide. We have to go grams of lithium hydroxide to moles of lithium hydroxide, to moles of carbon dioxide, to grams of carbon dioxide. So that's our plan of attack. So, we're going to need to know the molecular weight of lithium hydroxide and the molecular weight of carbon dioxide. We get that from looking at the molar masses, or determining the molar masses by looking at the atomic weights. Okay, so I'm going to show you how to do one, and then just give you the answer to the other. So if you remember, we'd have to look up lithium. It's lithium on the periodic table is 6.94 grams per mole. That's lithium. Oxygen, which is 16 grams per mole. That's the oxygen. And hydrogen, which is 1.01 grams per mole. If you add all of these up, you're going to get the answer of 23.95 grams per mole for lithium hydroxide. And you're going to do the same thing for the carbon dioxide. And when you do that, it's going to be 44.01 grams of carbon dioxide. Oops. Let me erase everything that was there before. Okay. So, now let's go ahead and we're going to figure this up. We have to go from grams of lithium hydroxide, 1.00 grams of lithium hydroxide. We know that every mole of the lithium hydroxide is equal to 23.95 grams. So this way our grams cancels out. Here's where we have to look at the stoichiometry. It takes 2 moles of lithium hydroxide that reacts with 1 mole of carbon dioxide. So that means we have 2 moles lithium hydroxide for 1 mole of carbon dioxide. And finally, the question was asking how many grams of carbon dioxide. So we have 1 mole of carbon dioxide, which was equal to 44.01 grams of carbon dioxide. You multiply by everything on the top. Oh, let's first check to make sure that everything balances. So we get rid of a grams of lithium hydroxide because we have one on the top and one on the bottom. We have a moles of lithium hydroxide on the top, moles of lithium hydroxide on the bottom, moles of carbon dioxide on the top, moles of carbon dioxide on the bottom, and we are left with grams of carbon dioxide. Unfortunately, it runs off the side there, which is what the question was asking for. Okay, so now we multiply by all of the numbers on the top, and you divide by all the numbers on the bottom. When you do that, you come up with the answer of 0.919 grams of carbon dioxide. So that tells you that for every gram of lithium hydroxide, you can get rid of 0.919 grams of carbon dioxide. So let's do another example. In this example, I've already given you the balanced equation, and what we want to find is if we start with 250 grams of aluminum hydroxide, and we only make, let me use a different color. If we only make 398 grams of aluminum sulfate, what is our percent yield? So once again, here you'd always want to check, but I've given you the balanced chemical equation, and I'm going to go ahead and give you the molecular weights for these, but you could check these on your own, but just due to time. The molecular weight of aluminum hydroxide, which you're going to need later, is 78.01 grams per mole. And the molecular weight of aluminum sulfate, because it's much heavier, it's a much larger molecule, is 342.14 grams per mole. You may want to write that down because I'm going to have to erase some of this in order to do our figures. Okay. So, first off, and let's use, this time I'm going to go to the correct number of significant digits in my final answers. Alright, so first let's determine what the theoretical yield of aluminum sulfate is if we start off with 250 grams of aluminum hydroxide. Okay, so we have 250 grams, whoops, which if you don't mind, I'm going to call this one A, reactant A, and this one the product B, just because I don't have much room to write. So this is a molecular weight for A, this is a molecular weight for B. We started off with 250 grams of A, with aluminum hydroxide, and we're going to try to eventually figure out the fact that what the percent yield is from 398 grams of product B. Alright. To go from grams to moles, we need the molecular weight of aluminum hydroxide, or A, and that was 78.01 grams of A is equal to 1 mole of A. It's supposed to be an M. And according to the chemical equation, 2 moles of A makes only 1 mole of B. So we have 2 moles of A makes 1 mole of B. Based off the molecular weight, we know that 1 mole of B is equal to 342.14 grams of B. Now let's make sure that everything cancels. The grams of aluminum hydroxide are the grams of A, moles of A, moles of A, moles of B, moles of B. So the only thing left is the grams of our product of B, which is aluminum sulfate. Okay, so if you multiply by everything on the top, and you divide, so we multiply by everything up here, we divide by everything down here, you get the answer of 548.23 grams. Which, if we're going to go to significant figures, we only need two significant figures. So that's 550 grams of the product B, which was the aluminum. Aluminum sulfate. Okay, so that's our theoretical yield. Now I'm going to have to do some erasing here so I can have room in order to determine our percent yield, which is what the question was asking for. So our percent yield is where we take the actual yield, which was given, and in this example here, I'll switch colors. We were given that we only made 398 grams of the aluminum sulfate. So we divide that by the theoretical yield of 550 grams of aluminum sulfate. Notice the units cancel out. There should never be units left on percent yields. Multiply everything by 100. And we get 72.36, which significant figures here would be 72%. So we have a 72% yield. You should do a lot of practice on those because it's so important to know how to do theoretical yields and percent yields. Now, just briefly, I want to discuss the different types of reactions that can occur, or some of the different types of reactions that can occur. One of the reactions is where you take two or more reactants and they combine together in order to make one product. So we have examples that include nitrogen and hydrogen making ammonia, propane and bromine making dibromopropane, and magnesium and oxygen making magnesium oxide. The opposite of a combination reaction is a decomposition reaction. That's where something breaks down into two or more substances. So, for example, we can have calcium carbonate making calcium oxide and carbon dioxide, potassium chlorate making potassium chloride and oxygen, and sodium azide making sodium and nitrogen. Finally, we have combustion reactions. Usually these are really fast reactions that can make a flame of some sort. And many times, at least here, we're talking about hydrogen and carbons, or hydrocarbons, that react with oxygen and air. And so examples include methane gas reacting with oxygen to make carbon dioxide and water. You can even have butane, like butane flame. You have propane gas, that reacts with oxygen to make carbon dioxide and water. Hopefully this has helped you learn how to do limiting reagents, theoretical yields and percent yields, and also just a brief discussion on some of the types of chemical reactions. I'll see you in class.